So I've done several videos that are answer problems like this with normal distribution applications. So I'm going to go through this one really quickly. But this is problem 3 from the test review. Red blood cell counts of women are normally distributed with a mean of 4.5 and a standard deviation of 0.3. So what that tells you right away is that you can predict these. You can predict a lot about this data by looking at the normal curve. We know here inside that normal curve the mean and the standard deviation will be given to us, and it was right there. So our standard deviation of 0.3 and our mean of 4.5. So now what we've got to do is we've just got to take that curve and we've got to use that curve to answer multiple questions. First one, A, is asking about the probability of a randomly selected woman that has a red blood cell count below 3.9. So I'll go ahead and use the red to answer A here. So I'm going to mark my 3.9 somewhere right about there. Oh, that was a bad line. But I'm going to go with it. So there's my 3.9. And I want to know something below that. So I'll shade here to the left of that line. That's what I'm looking for. I'm looking for the area. So what I can use is I can use the calculator to give me the area under that curve. If you're stuck on the exam and you don't know how to use the calculator to do this, if you wanted to write something like the area under the curve from some value to another value and put that as a sentence, you'll get most of the credit. But if you wanted to use the calculator, remember this is going to be the normal CDF because you're measuring the cumulative density function under that curve. You're starting at about a negative 10,000, just all the way over to the left somewhere. We're going to go up to the point that we're looking for. In this case, that is 3.9. And then we're looking at a mean of 4.5 and a standard deviation of 0.3. So that's what you have to type into the calculator. When you type that in, you get a value of 0 or 0.0227 or roughly 2.27%. So the chances of getting a female that's below 3.9 is about 2.27%. Next problem, B, find the probability of a selected woman that is above 5.1. I'm going to go and use the same curve. I'm just going to use a different color here. So I'll say that this case, I'm going to be looking at above 5.1. So I'm looking for this blue area under that curve. Again, if you wanted to just write out the words, I'm looking for the area under the curve from 5.1 up to 10,000. You could do that. But we do have the calculator that can help us solve for that area. And we just type in the, to use the formula, we're going to use normal CDF. To use the function on the calculator, sorry. And we'll be starting here at 5.1. And we're going to go to 10,000 or something very, very large, well above the values that we're looking for. The mean and standard deviation did not change, so that's going to be 4.5 and 0.3. When you type that in the calculator, you should get roughly 0.0227 or 2.27%. All right. So the next question is, what is special with answers in 3 and 4? They're equal. That's really important. Notice they are the same. I'll just put equal answers because they're the 3. Is this a coincidence? It's not a coincidence because they're the same value above and below the standard deviation. Let me talk about that for a second on this curve. So I'm going to talk about this in green here. So I look at this curve. What you'll notice is there's a distance between that mean and the lower limit, and that mean and the upper limit. And by lower limit and upper limit, I mean 3.9 and 5.1. If you look at that, you know that there's a distance between the mean and this 3.9, and that distance is roughly a 0.6, 0.6. Same idea for the 4.5 to 5.1. It's a distance of 0.6. Do the math and it makes sense. It's the same way. Now there's something special about that 0.6 because if you look at the standard deviation, that's 2 of the standard deviation. So what's really happening is I'm starting at the mean and I'm adding 2 standard deviations to get to the 5.1, and I'm subtracting 2 standard deviations to get to the 3.9. So what I'm really looking at is I'm looking at the data outside 2 standard deviations, and that's roughly 2.27% and 2.27%. So when you add those two together, there's roughly 5% of the data outside 2 standard deviations. That is, by definition, the empirical rules. So that is why it's not a coincidence. So if you really wanted to come in here and type all that up, you could. I'll type it up really quickly in a text box. All right, so I typed up an answer. It's hard to read because of that equal word in there. But because the limits for number 3 and number 4 are based on 2 standard deviations away from the mean of our data, we know that outside those limits, there's roughly 5% of the data And our numerical answers of 2.27 plus 2.27 seem to align with this conclusion as well. So that kind of explains why why that's no surprise to us. All right, so continuing on. What percentage of women have red blood cell counts in the range of 4.2 to 5.4? Hopefully you can see where I'm going with this problem, but let's go ahead and prove it mathematically. I'm going to go ahead and utilize a normal curve, a new normal curve here, because I know that this data is normal, but I want to make sure that I've got my reasoning correct. So again, if you're not utilizing a normal curve on each one of these, I would recommend you draw a normal curve because it's going to make things much better for you each time. Go ahead and identify my mean and my standard deviation, just like before, and then I'm going to identify the region of the curve that I'm looking for. In this case, I'm looking for the region from 4.2 to 5.4, so I'll go ahead and mark off that region. 4.2 is roughly here, and 5.4 is roughly here. So I'm looking for the number of women that are the percentage of women that exist within this range. So I'll go ahead and identify that region that I'm looking for, and I'm looking for the percentage of women that fall within this blue range here. So again, this is going to be a normal CDF problem. I'm looking for the area between two values, so I'm just going to be utilizing the function in the calculator that calculates the curve, the area between the normal curve, the cumulative density function, running in this case from 4.2 to 5.4, 4.2, 5.4, standard deviation of 4.5, and the mean of 4.5, and the standard deviation of 0.3. When you calculate that into the calculator, if you type that in just like that, you end up getting a value of 0.839994, so it's roughly 84%. So there's roughly 84% that fall in between those two values. The reason I was saying you could probably do this in your head immediately is because you can use the empirical rule to estimate that, but we're going to go ahead and just go with 84%. All right, for number 4, I'm going to go ahead and just give the answers to the first few problems on this because we've done several problems like this, whether on this video or other videos. So I'm just going to put the solutions for the answers for A, B, and C, and then I'll actually walk through D and E. All right, so there are the 3 answers and solutions for A, B, and C. Hopefully those make sense. If you still need some help with that, watch this video clip again from the very beginning or look for some of the other normal distribution application videos that are out on my YouTube channel. So let's go ahead and continue with the D and E. These things look a little bit different. It's still dealing with men's and women's heights that are normally distributed. So what I'm going to go ahead and do is I'm going to go ahead and draw 2 curves, one corresponding for the males and one corresponding for the females. So here's going to be my mean for the males, and then I will put right below that the corresponding curve for the females. So here's my curve for the mu of the females. All right. The value for the males is going to be 69.5, and then the value for the females is 63.8. Standard deviation is 2.6, and standard deviation for the male is 2.4, I believe. All right, so now this problem's a little bit different because what I'm looking for is I'm looking for the height that separates a percentage. Well, the first one's talking about the bottom 90%, and hopefully you can see. I'm just going to draw up, I'm going to draw a line that refers to the place that separates the bottom 90% and the top 10%. And it's this kind of this blue vertical line right about here. If you look to the region to the right of that, I'll color this in with the red. This red region is the area. This is the top 10%. It's the top 10% of the region. So that is the area that I'm not interested in. I'm interested in this region to the left. And really, I'm not interested in either of the regions. That's kind of a false way to think about this. What I'm really interested in is I'm interested in the value that separates these two regions, this z-score or this data. That's what I'm looking for, that value. It's the exact same thing when you look at the females. There's a value point that separates the top 10%, again, highlighted here in red, and the bottom 90%. There's a value somewhere along that horizontal axis that is, and we've got to figure out how to find that value. Luckily, we've got 2 functions that'll help us on those calculators. We've got normal CDF, which will always be given some limits on what you're looking for. It'll return an area. And we've got a function that's called inverse norm. Now, inverse norm acts differently. Inverse norm, if you give it an area, a percentage, a probability, it will return and a value, and that's exactly what we're going to do. I'm not going to film my calculator here, but I'll walk you guys through it. I'm going to press the on button, go to my distributions, second vars, I'm going to go down to inverse norm. It asks me for the area. Well, I can do this in two different ways. I could look, let me back up. Let me do it this best way possible. I'm looking for the bottom 90%. Inverse norm is going to ask for three numbers. The first number is going to be the area to the left of that value that I'm looking for, and then it's going to ask for the mean and the standard deviation. Well, if I'm looking for the bottom 90%, I'm going to look for the area to the left. So it's going to be that blue area, which is that bottom 90%. So I'm just going to type in 0.90 as my area that I'm looking for. My mean and my standard deviation are going to change depending if I'm doing the female or male. I'll just go and write up the male here, 69.5 and 2.4. Once I type that in, I should get a value of 72.58 when I round that. 5.8. And you should be thinking to yourself, what is this value? Is that a percentage? It's not. Because remember, this is that value that's on that horizontal line. This is a measurement in inches, and that's very, very important because this 72.58 is the measurement that separates the bottom 90% to the top 10%. That's what's really, really cool about it. If I wanted to repeat this process for the female, I would just use the same function, inverse norm. I'm going to be using the same value, 0.9. The only thing that changes is going to be my standard deviation and my mean. In this case, that turns into 63.8 and 2.6. When I end up calculating that for the female, I get a measurement of 67.13. And again, remember this is inches because that is that measurement that's going along with that limit that separates the bottom 90% to the top 10%. I'm not going to draw out E, but I will. So let me just refer back to it a second. This was all D. I did D here in yellow. This was all D. I'm not going to walk through E. I'll just give you the answers to that one. I think that you guys can follow the process that I did for D and solve E on your own. But I'll go ahead and put the answers here just in case. All right, so for those last two, I'd have the inverse norm again. We're looking for 5% of the data, or there's a value that separates 5% of the data. And then I've got the new standard deviation and mean put in there as well. I'd calculated both of them again. The male height separating the bottom 5% would be 65.5 inches, and the female would be 59.5 inches.